Hello everyone and welcome to the section of the phenols. We were discussing with respect to the chapter of alcohols, phenols and ethers. So in the section of the phenols, we will proceed with respect to the properties. So when we discuss about the properties of phenol, right? Now when we take a look at the phenol, this particular phenol is composed of the two different parts. One is the benzene type of the system or the aromatic system, or what we call it as an aryl group, and the another one is the hydroxy group of it. So when we take a look at the phenol is made up of two parts. The first one is the aromatic system, that is your aryl group. And to this aryl group we have the most important functional group attached, and that is the hydroxy group, and therefore the second part is the hydroxy group. Now here we need to understand that majority of the properties of the phenol is because of this particular hydroxy group which is attached to the benzene type of system. Thus, if we consider different types of properties, it is mainly because of the presence of the hydroxy group. Let us start with a few of them. For example, the first one, let's say about the solubility. So when we speak about this solubility, the solubility of a phenol in water is because of the presence of the hydrogen bond that it is going to generate in water. So when we take this particular phenol, and as we insert this particular phenol in water, what happens is that this particular phenol generates the hydrogen bond with the neighboring water molecules. Because of the presence of these hydrogen bonding, we can say that the phenols are soluble in water. So when we take a look at the solubility as a property, it is all because of the presence of the hydrogen bonding. Now the hydrogen bonding comes because of these particular polarity that is generated between the oxygen and the hydrogen there. Correct. So this is the first property, as that is the solubility is concerned. Second property is with respect to the acidity. Now when we speak about the acidity of phenols, we can understand that by two major reactions. One is that the phenols readily react with active metals. What do we mean by active metals? Active metals are the metals such as sodium, lithium, potassium. Okay, so therefore these particular phenols readily react with active metals. Let us take one active metal such as sodium. Okay, so when it reacts with sodium, it will form the sodium phenoxide. That is, sodium with a positive charge and the phenol with the negative charge over here. Okay, so this part is a phenoxide. Of course, this becomes a sodium. So what we have is the sodium phenoxide. Now when we try to balance this entire reaction, this hydrogen usually evolves out as a hydrogen gas. So therefore, as we have two hydrogens there, we'll take it over here as the two phenol molecules. Now two phenol molecules react with the two sodium, therefore giving rise to two sodium phenoxides plus hydrogen is generated. The second reaction is of these particular phenols with aqueous solutions of active metals such as sodium hydroxide. Again, we are going to get the same product over here. That is, when the phenols react with aqueous solutions of sodium hydroxide, sodium phenoxide is obtained, O minus Na plus. So what we get over here is the sodium phenoxide. Okay, but this time we need to observe the byproduct. Here the byproduct that we obtained was the evolution of hydrogen. Over here, on the other hand, this hydrogen combines with this particular part, the part of the OH, leading to the formation of H2O. Water is eliminated. Now these two reactions wherein the phenol is reacting with active metals while the phenol is also reacting with the alkali. Right? So these two particular reactions indicate that the phenols have acidic characters. But on the other hand, the phenols fail to react with sodium hydrogen carbonates. Or here, when it fails to react with sodium hydrogen carbonate, that is the sodium bicarbonates, it will show that phenols they have the acidic characters. Though they have the acidic characters, but they are not acids. Okay, though they have the acidic characters, but they aren't the acids. This is what we need to understand here. Okay, now speaking about the acidic characters, let's see why do these particular things have acidic characters. Now, the answer for the acidic character lies how is the OH connected to the aromatic system. When we observe the connection, that is, when we observe the carbon connected to the OH group, this particular carbon is sp2 hybridized. Hybridization is sp2. Now this sp2 hybridized carbon is electron withdrawing in nature. It is electron withdrawing in nature, that means it will tend to take the electron density from the oxygen towards the benzene system. As a result of which, a polarity is generated between oxygen and hydrogen. Okay, because the electrons are dragged towards this particular phenyl system, the oxygen and hydrogen bond, what is connected to the carbon, this carbon of course is an sp2 hybridized carbon of the ring, right? Now as this fellow carbon over here drags the electron towards itself, it generates the polarity between the carbon and oxygen. As a result of which, it induces this oxygen to get ionized. And we will see that this entire thing is going to leave the hydrogen away. Thus, when we observe, because of the sp2 hybridized carbon which acts as an electron withdrawing group, this particular phenol gets ionized to a phenoxide ion. A phenoxide ion is nothing more than your benzene system connected to oxygen having a negative charge. Now, a phenoxide ion is formed along with H+. Now, this particular process is a reversible process. Keeps on happening repeatedly. Right? Now, as this phenoxide ion is more stable than the phenol itself, it tends to leave, it tends to give out hydrogen in the form of protons. Because of the particular presence of H+, the solution tends to become acidic. Right? So therefore, we'll observe now what is the condition for the stability. How come this particular phenoxide ion is more stable than the phenol? Right? Now, speaking about the acidity of the phenols, ionization of a phenol. Now, as we already know that this particular phenol undergoes an ionization. It undergoes ionization to produce a phenoxide ion right, along with H plus, that is a proton. We need to understand that how come this particular phenoxide ion is stable. This phenoxide ion which is formed, it is stable because of the presence of resonance structures. This molecule what has been formed, it undergoes several structures of resonance. So more the number of resonating structures we have, more stable that particular phenoxide ion becomes. Let us observe the resonating structure of this phenoxide ion. Now, as we have this particular phenoxide over here, let's say this is an oxygen with negative charge. Now, these electrons will enter here. The moment it enters here, these electrons will shift up. Right? Now, as they shift up, what we are going to have is the oxygen generates a double bond. It generates the double bond with the carbon over here. These pi electrons have shifted, so a negative charge is generated here. The other two bonds, we are going to keep it undisturbed. Let's keep it here. Right? So this is the resonating structure over here, what we have got. Now, let's enter this particular electrons inside. These pi electrons will shift their positions. As these pi electrons will shift their positions, we have the negative charge here. These are the electrons over here. This is a double bond oxygen over here. Right? Let us see what happens further. These electrons will enter inside, as well as these pi electrons will go outside. As they go outside, we have our next resonating structure. The structure wherein we have this particular bond here, the second bond here. This pi bond has been delocalized. It comes over here. This is oxygen over here. Right? These electrons will travel inside. These pi electrons will get back to oxygen, giving back the final resonating structure. So what we have is 1, 2, 3 oxygen now with a negative charge. Right? So the number of resonating structures that we have is 1, 2, 3, 4 and 5. As the number of resonating structures increases, quite simple, the stability of that particular phenoxide ion goes on increasing. This is how the stability and the resonating structures are interconnected. Okay, now suppose we have this particular phenoxide ion. Let's say this is the phenoxide ion what we have, right? Now, at two positions, mainly at the para position and at the ortho positions. These are the ortho position, this is a para position. Am I right with this? Now, in case if we attach any electron withdrawing group, such as we can say with respect to NO2 group. If we attach this NO2 group either to the ortho position or either to the para position, what it does is a simple thing. It takes the electron density from the benzene ring. Now, benzene ring is connected to this particular oxygen. Correct. So, in case if this particular phenol is there, okay. Now, if we attach ortho at the ortho position or at the para position, the electron withdrawing group such as NO2 group here, it will take the electron density from this particular aromatic system. It will make sure that this particular bond becomes more polarized because it is dragging those electrons towards itself. As a result of which, the bond between oxygen and hydrogen becomes more polar because it is sending all the electron towards the electron withdrawing groups. Either we attach electron withdrawing group to the ortho or to the para. What it does? It will take all the electron towards itself, thereby making this OH group more polarized. More polarized OH group or the bond between oxygen and hydrogen becomes, more is the generation of phenoxide ion takes place, because more easily that particular hydrogen is removed out in the form of proton. Similar effect but an opposite way, it goes when we attach electron releasing groups. Okay, so at one time what we can say is, if we have an electron withdrawing group attached, if you have any electron withdrawing group attached at ortho or para positions, what it does is, it will take away the electron density from the system, from the aromatic system, thereby making the OH bond more polarized in nature. Okay, the moment it becomes more polarized, that means it has more tendency to exist as a phenoxide ion. Easily the hydrogen goes out in the form of proton. Okay, thus the phenoxide ion is readily formed, right? Thereby, any electron withdrawing group attached either to ortho or para position, it is going to increase the acidic character. On the other hand, if we are going to attach electron donating group, any group such as an alkyl system, CH3, C2H5, such kind of things. Okay, so any electron donating group attached. Now what does this do is, it will keep on releasing the electron, it keeps on giving the electron to the benzene system. As a result of which, this particular bond is not so ionized, it's not so polarized. Even though if the phenoxide ion is formed, the phenoxide ion is destabilized. Okay, so these particular things keep on releasing these are electron releasing groups. So these electron releasing groups, what they are going to do is, they simply destabilize the phenoxide ion. They are going to destabilize the entire phenoxide ion in this case. Okay, the moment they start to destabilize the phenoxide ion, it's quite simple that the acidic character in this particular case is going to decrease. So in short, electron withdrawing group increases the acidic levels. On the other hand, electron donating group decreases the acidity of a phenol. Electron withdrawing group, they are going to enhance the stability of phenoxide ion, while electron donating group, electron releasing group, they are going to destabilize the phenoxide ion. So once the phenoxide ion is destabilized, acidic character is going to decrease with respect to the phenols when electron donating group, or we can say as electron releasing group, is attached to it. But the attachment should be again at the ortho or a para positions, right? So this is about the effect of electron donating and electron donating and electron withdrawing groups. Now when we compare these things, that is the acidic character of a phenol to the alcohols. If we consider an alcohol, ROH. Okay, now in this particular case, again R is an alkyl system. Alkyl systems are again electron donating groups. Okay, as a result of which RO minus plus H plus. Okay, though the H plus are formed, when we compare this particular reaction, that is the ionization, in order to form the alkoxide ions. Okay, now when we observe the stability of an alkoxide ion to the stability of phenoxide ions, okay, plus H plus, right? Now alkoxide ion and phenoxide ion, now it all goes with respect to the stability. If you want to understand who is more acidic, we need to understand who is more stable. More stable the ion is, the more is the acidic level, because more easily it is going to generate H plus. So when we compare the stabilities, alkoxide ions are less stable when we compare to the stability of a phenoxide ion. So as phenoxide ions are more stable than alkoxide ion, H plus is generated, protons are generated more readily in the phenols than compared to the alcohols. As a result of which, alcohols are comparatively less acidic to phenols, because phenols are going to give us phenoxide ion. After ionization, it gives us a phenoxide ion. Phenoxide ion is more stable compared to that of alkoxide ion. Therefore, the phenols are more acidic compared to that of alkoxide ions, right? So this is all about the acidic characters. Let's proceed with the next section. So the next point of our discussion is with respect to the esterification. Now, when we take into consideration of esterification reaction, esterification of phenols. Phenols usually react with the acid anhydrides under the presence of acids. Acids such as we require sulfuric acid. Under that particular consideration, what happens here is the phenols will react in order to give the product, that is CH3, CO, 2 times O. So therefore, this is acid anhydride. Okay, so this reaction occurs under the presence of concentrated sulfuric acid. Under the presence of the concentrated sulfuric acid, this half section in a sense, we have CH3, we have C double bond O, oxygen over here, C double bond O, CH3, right? So this particular part, okay, this particular part, or we can say as this particular part over here, is going to replace this hydrogen. The moment it replaces that hydrogen, we are going to get our first product, and this particular product is O, C double bond O. Therefore, it is connected to this carbon, right? This is connected further to CH3 there. Thus, what we get over here is phenyl acetate plus what we have left over is going to be the other part of this. What is the other part that we have is this one. This oxygen takes up this hydrogen. So therefore, what it happens to give us is CH3COOH. So therefore what we get over here is the acetic acid. This reaction of the phenols, with acid anhydrides under the presence of concentrated H2SO4, in order to give us a product, phenyl acetate, and a byproduct, acetic acid. We call this particular reaction as acidification of phenols. This is our first reaction. As we proceed further, the next part, what we need to observe, is the electrophillic substitution reactions. Now, let's try and understand this. When we have a benzene system, and this benzene system is connected to OH group, of course we have this as phenol. This particular OH group activates two positions. That is, it activates the ortho positions and it will activate the para position. It will activate these particular positions. It will activate these positions for the electrophilic attack. That means the electrophiles what we have, these will tend to attack at the ortho or at the para positions. Okay, so there are several types of the reactions in this which we are going to take a look one by one. So first one, let's observe. Let us observe the reaction of phenols with dilute nitric acid. Okay, so when we take a look at this particular reaction, let's say over here we have the phenol. This upon reaction with dilute HNO3. What we have for this is the dilute HNO3 gives rise to NO2 as an electrophile. So the electrophile generated in this particular course of reaction is NO2. NO2 will react with the phenol at two positions. One at the ortho position over here, that is OH, and here is the NO2, right? So this is our first product, that is the ortho nitrophenol. Plus, in the second set of this reaction, NO2 group which has been produced, we will attack at the para position. When it attacks at the para position, we have this particular product over there, wherein we have OH attached over here and NO2 attached over here. So this is our para nitrophenol. Okay, so we have these two sets of products over here. One is the ortho nitrophenol and the another one is the para nitrophenol. We need now to understand about the boiling points of these. If you observe this ortho nitrophenol, okay, let's take this particular ortho nitrophenol over here. This is our oxygen connected to hydrogen. Let's say this is the nitrogen connected double bond oxygen, single bond oxygen over here. This is a negative charge. Correct. Now what is going to happen here is this hydrogen is attached to electronegative oxygen in the case of ortho nitrophenol. Okay, what will happen here is as the hydrogen is attached to electronegative oxygen, it will generate the hydrogen bond. This hydrogen bond is formed within the molecule itself. Okay, hence this hydrogen bond we call it as intramolecular hydrogen bonding. Now, whenever there are compounds phenols are usually having less boiling point. Thus, orthonitrophenol is usually a steam volatile. Okay, that means you can simply pass the steam to this orthonitrophenol, and from that particular product orthonitrophenol gets evaporated. We can condense it and we can separate it. Okay, so the reason behind orthonitrophenol's lower boiling point, okay, this thing has a lower boiling point, is because of the presence of the intramolecular hydrogen bonding. Okay, now when we observe about the para-nitrophenols, let's over here that we have the oxygen, hydrogen, and let's say this is the NO2 group over here. Let us take another orthonitrophenol. Okay, let's say this is OH. Let's say this is the NO2 group. Okay, nitrogen, double bond oxygen, single bond oxygen over here. Now we have taken into consideration of two molecules of the para-nitrophenol. Now in this case, there is a hydrogen bond that is created between the hydrogen attached to electronegative oxygen and of course even here one. Correct. Now between this electronegative oxygen and between this hydrogen, what we have is, this is our intermolecular hydrogen bonding. Okay, therefore, here in this particular case of para-nitrophenols, the boiling points are usually higher. Right? So, we have two different aspects now. When we are considering this particular nitrophenols, if it is an orthonitrophenol, because of the presence of intermolecular hydrogen bonding, intramolecular, within the molecule itself, it is not getting connected to the another molecule. Due to this, this is a steam volatile. It has lower boiling point. When we observe about this particular para-nitrophenol, between the two different molecules, there exists a hydrogen linkage. Because of this particular hydrogen linkage, which we call it as an intermolecular hydrogen bonding, what happens is this particular molecule is going to show us comparatively higher boiling point to its counterpart, that is the orthonitроphenols. Right? Coming towards the next reaction, and the next reaction is the reaction with concentrated HNO3, that is a nitric acid. So when we have a reaction of the phenols, when we have the reaction of phenols with concentrated nitric acid, let's take it a little bit lower. Okay, so when we have the reaction of the phenols with concentrated nitric acid, here we get a single product. But in this particular single product, the electrophiles, that is the NO2, are going to attack at all the three positions available. All the three positions available, that is the two orthos and one para position. So let's observe this one. So when the phenols will react, we will have a product over here as OH, NO2, NO2, and of course another NO2. Right? So here is where we have 2, that is a position number 2, position number 4, position number 6. So 2, 4, 6. Tra, nitro, phenol. Okay, so this is the first one. As we observe the further reaction, that is the halogenation. Now, before proceeding with the halogenation, let us try and understand here, the 2,4,6 tritryphenol is also called as the picric acid. Okay, and now because of the presence of the 3 electron withdrawing group, picric acid is more acidic compared to the phenols. Okay, that are the small points what we need to understand. Now, coming towards the halogenations. In the halogenation reaction, let's take into consideration of our first reaction, that is when we have the phenols and the phenols will react with bromine, Br2, under the presence of chloroform. So what we have here is the OH over here and Br over here, the first monosubstituted product, that is the ortho bromophenol. And the next product that we have is OH over here and Br over here, that is para bromophenol. Right, so we have the 2 products over here. One is the orthobromophenol, second one is the para-bromophenol, the monosubstituted products which we have obtained. Right? On the other hand, when we react these phenols, with bromine water, that is Br2 in water. Okay, we get over here tri-substituted product. Here comes the OH, here is the Br, here is the another Br, and finally here is the another Br. So 1, 2, 3 Brs at the position number 2, 4 and 6. So therefore 2, 4, 6 tri bromophenols. Right? So proceeding further. With the next set of reaction which we have is one of the most important reaction. It is to be pronounced as the Kolb's reaction. Okay, so the Kolb's reaction. In the Kolb's reaction, what we do is we take the phenol, react this phenol with sodium hydroxide. So when we react with sodium hydroxide, eventually we get an intermediate, and the intermediate is going to be sodium phenoxide. Okay, so in the first case, what we are going to do is we are going to take a phenol. This phenol is going to be treated with sodium hydroxide in order to yield the sodium phenoxide over here, O minus Na plus. Right? So sodium phenoxide. Now this sodium phenoxide, once we take further, when it is reacted with carbon dioxide, okay, under the acidic conditions, we end up having over here OH, EOOH. Therefore, we end up having salicylic acid. So, the Kolb's reaction, one of the most important reactions, is nothing more than the formation of the salicylic acid formed with phenols. Phenols are reacted with sodium hydroxide in order to yield sodium phenoxide. Sodium phenoxide are reacted with carbon dioxide under the presence of hydrogen in order to yield salicylic acid. right? So this is one of the most important reaction you can expect for a 3-mark subdivision, of course, along with the statements. Right, next one, and that is one more important reaction. The Reimer-Tiemann reaction. One of the most important reactions that we have. The Reimer-Tiemann reaction. So, in the Reimer-Tiemann reaction, when we react the phenol, when we react this particular phenol with sodium hydroxide under the presence of chloroform, what happens is it will give us an intermediate. This intermediate, O minus Na plus, of course over here is CH2Cl, substituted benzyl chloride. Okay, now this thing upon reaction with NaOH, it will yield the compound O minus Na plus. This particular point over here, that is CH2Cl, gets oxidized. It will get converted into CHO. Alright. Now, this one, further on acidification, we will end up having over here the final compound, that is OH. This particular thing gets hydrolyzed, and over here we have CHO, and that is the salicylic. Also, this is salicylic. This is the salicylic dehyde. So, Reimer-Tiemann reaction is nothing more than the formation of the salicylic from the phenols. It includes the reaction of the phenols with sodium hydroxide under the presence of chloroform. In order to give the intermediate is substituted benzyl chloride. This substituted benzyl chloride further on reaction with NaOH, it is going to yield a compound having CHO, aldehyde group at the ortho position, which further on acidification ends up giving us salicylic. This is how the entire process goes. In case, if we replace the CH3Cl by CCl4, that means instead of taking chloroform, if we take over here into the consideration of carbon tetrachloride, we will get over here, that is the final compound as salicylic acid. So remember this. One small change over here changes the particular product from an aldehyde to an acid. Okay, so this is the Reimer-Tiemann reaction. So proceeding further with the next reaction, that is reaction of phenols with zinc dust. Okay, so let's take into consideration of phenol. This particular phenol is reacted with zinc dust, upon which zinc takes up this particular oxygen. In short, it is reducing the phenol in order to give rise to the benzene with zinc oxide. Right? Now, when we observe the next set of reaction, that is the reaction of phenols with oxidizing agents, that is nothing more than the oxidation reaction. Now, the phenols usually react with chromic a combination of sodium chromate along with concentrated sulfuric acid. Okay, so when we have the phenols, these are the phenols. When we react this one with Na2Cr2O7, sodium chromate, under the presence of concentrated sulfuric acid. Okay, what happens is the phenols get converted into diketones. Diketones are nothing more than the compounds having two ketonic groups. So therefore, this one gets converted as C double bond O, C double bond O over here. This is a diketone which is called as we call it as the benzoquinone. Alright, so here is where we end up all the reactions with respect to the phenols.